S composed R. It is S composed R. That is the composite relation. Okay? And so first is R. We usually, so S composed R is a relation between A and C, and we usually write it instead of the set form also. So this means there exists a B from B such that first is R. So A, R, B, and then it is C, S. Okay? So the first, so it is written in the, so observe this reversal of notation. And there is a lot of history behind this. Previously, people used to use R composed S and so on. Still, some people use R the other way round, and most people use this reversed notation, and later on we will, when we will do much later on in, if we do category theory, we will understand why we do this. So there is a reason behind choosing this kind of a reversed notation, but you have to be careful. So that's what I can say at this stage. So that's one thing. So now let's come to theorem 4.2. Any questions with those? Equations 39 to 45. Let's try and see one of them, say 40. So this is how you should proceed with your proof. And what did I say? S and U. Okay, so it is the other way around. U is A cross B. And this is C cross D possibly. Right, yes. So then, let's see what is R composed S composed U. So let's see. So I take an A from A and say a D from D. So this happens. By definition, it means that there exists. So first S composed U. S composed U is from A to C. And this is, so there exists a C in C such that A S composed UC, and then it is RD. This sentence is actually a conjunction. It means A S composed UC and CRD. Okay? So this means, this is the same thing as saying, this already was there, but this part says that therefore there exists a B in B such that AUB SC and RD. Okay? Clear? Are you? Am I clear, or do I need to say it again, or expand on it? Yeah.
It's fine.
Okay.
It's fine.
So this therefore is equivalent to saying both are there exists. So it doesn't matter which one you choose first. So it means that there exists a B in B and there exists a C in C, such that the same thing is happening. A, U, B, S, C, R, D. Okay? So therefore, this statement now means, first if we apply this part, there exists C part. So this means there exists a B in B, and this means A, U, B, and this is R composed S, D. Okay? So now this means same thing as A, this is R composed S composed U, D. Okay? So this is where one minute this is where you applied the definition of composition. This is again where you applied the definition of the composition. This is a logically equivalent. This is where you applied the definition of composition, and this comes again by the definition of composition. So you see, the moment you see this proof, if you present it in this way, there is no words, no use of words, nothing. It is just a symbolic manipulation around your logic. And it makes the proof very, very clear. Okay? So, I would suggest you try to write proofs in this symbolic manipulation style. Okay? So, slowly you will, after the end of this course, you will come to believe, well, that mathematics is nothing else but logical manipulation of certain formulas. All the words and names that we give are just like names given to us. Some structure is over here called Partho, some other structure is called Julia, some structure is called Charles. It doesn't matter, Charles, the name of Charles could be given to someone else, and that's just a name. So we just give names to make our lives simple, to handle these formulas in a nice way, but it is just syntactic manipulation of formulas. And that makes it very, very clear and without any ambiguity. Okay? Is this clear?
Yes.
Yeah. So you would,
Yes, thank you.
yeah, you would like to, I would promote this way of presenting proofs in this syntactic style. Okay? So that is what you should present. Okay, now for the others, for the other equations or inequations, any questions, queries?
Doctor, I've got one.
Yes.
On page 12, where we're looking at the employee and the database.
Yes.
If Dr. can just highlight or explain the B op and of the identity of the I. It is just a bus theorem 4.2.
Yes, yes.
Where we actually get maybe a list of the identity numbers with the division as well as the surname, the initial.
Yeah,
and
yeah.
employee.
Is it B op? Was that the relation B, right?
Yes.
Yeah.
That is
B
B op.
B is, okay. So let's see, B is the database of employees and divisions, right? So
Yes.
EBD means employee E works for division D, division small d, right?
Okay.
That is what we started off with. So now, and I and D. What is I? NID. So this says there is a person, I don't know, but I am not sure about his or her name, but some identity number that identity number is in division D, right? So now what is B op composed I? So I is all identity numbers and divisions, and B op is divisions and this, right? So what does this mean? So B op composed I is a relation from identity numbers to employees. So when shall I have something like this? When shall I have something like this? This is meaning that there exists a D in D, this is just the definition, such that NID and B op E. Right? See, EBD means this is the same thing as saying D B op E. Right?
Mm-hmm.
So it means, so which pairs? So actually this means B op composed I only has the identity number and the name and the full and the employee. Identity number, employee. Okay?
Yeah.
Provided, so it is just not that, provided the identity number, the corresponding person, works in some division. So that's the, so NE, provided N and E are related, so the person E has the identity number N, that is for always sure. But here in this database we will have that pair only if that employee and hence his identity number is connected to a division. Tomorrow if he leaves it, this pair will be just taken out of that database. Right?
Okay.
So although E has N and E are tagged together always, because that is the South African identity number, say, that is given to him or her forever, wherever he is. But it is in this database, provided there exists a division where this employee works, a division of that company where this employee works. Okay, so it is not the collect pair of all those pairs or identity numbers and the name of a person. Not everyone. It is connected with the divisions of this company. Okay, so that's how. But we need not. My whole argument here was I need not actually keep this information in my database. I can create this always from this database and this database. I don't know if you are familiar with databases or not. You will possibly hear this word something is called the key of the database, right? And the key is unique, right? So here in this example, n, I mean to say this,
Identity number.
yeah, the I, the employee identity number. So this I, this relation I is always the key. The column which is the key is for n, which is these identity numbers. So that connects uniquely with everything, every database of that, right? So I gave an example of a key thing, but you can always have others also, other composites also made out. And that is, they are often called composite tables. Databases are usually represented as tables, and you have composite tables. So you don't keep the composite tables, you just keep the basic ones. You just store you just store B, I, and such things. You don't store every composite. You can always create it out of it. And that's a simple algorithm to create it. Okay? So that's how composites come into picture in applications, where it tells us that composite is something which can be made out of the other given things. So why spend your resources in storing it? Just store the basic entities of the data set. Okay, that's how composites come into picture in applications. Yeah. Next.
Thank you, Doctor.
So, Theorem 4.2, all those equations 39 to 45. So, I believe they should be clear, right? I don't know. I mean to say, you think you will be able to write their proofs, right? Okay?
Yeah, we'll try.
Yeah, sure.
We'll try.
I have given only a proof of 41 and 44. Yeah? You see, it's also that syntactic way of writing. So I've already given examples of that proof. I gave another one. Now you should be able to write the others. Okay? Now, let's come to the next. Do you have a remark 4.3 there? Just after Theorem 4.2, do you have a remark 4.3 or a definition 4.3?
Definition. Definition 4.3.
Okay. So this is something which I added later on. I'll also put up this upload. As I said, this is getting bigger and yeah. So that's just a remark, but we will see more of it later on. Okay. Next definition. Any questions on this? Did you understand the definition?
I did, yes. Thank you.
Okay. The rest?
Doctor, the one on the E, the trichotomous.
Yes. Trichotomous. Yes. What is your question?
Yeah, if Doctor can just give us some indication as to how that particular one works.
Think about less than or equal to.
Mm-hmm.
Think about, for instance, not less than or equal to, less than on numbers.
Yep.
You take any two numbers, say 4 and 5. 4 is less than 5.
Yep.
But 4 is not equal to 5 and 5 is not less than 4. Okay?
Okay.
So take any two numbers, exactly one of these conditions, either xy, x is less than y, or y is less than x, or x is equal to y.
Okay.
So there are exactly three possibilities. Now if you generalize, either x is related to y, or y is related to x, or x is equal to y. Okay, exactly one of the three conditions is going to hold good. So that's where. Now where does it come? So let's take an example where it doesn't happen. So trichotomy just it's just a three version of what is known as a dichotomy. If you look into the English word, dichotomy means there are two options and one of them will happen, the other will not. Okay, and here it says there are three options and exactly one of them will happen, the other two will not. Okay, now what does trichotomy say? So what does trichotomous mean? It just says if you take any two elements from A, it says either x is related to A. So what are the three conditions? One is this, one is this, and one is this. Now, well, if you take any two, either they will be equal or they will not be equal. Good, that's always true. You always have this dichotomy. Wherever you are, either x is equal to y or x is not equal to y. Okay, that's always. So if x is equal to y, you are done. If x is not equal to y, this one is further divided into two cases. That means is either x is related to x r y or y r x. So it's saying something like either x is less than y or y is less than x. It's saying something like this. Okay. So in general, therefore, I can say that if you take any two elements, either they are equal or they are related. So it is never possible to take a pair which will never be related. So in general relations, that can be the case also. So for instance, you take any set A and take its subsets, set of all subsets. So even if you try to see it diagrammatically, it is also possible. Subsets were subfigures of this. So here is one subset and here is another subset. They are not related. Neither A, if you take x and y, neither is x a subset of y nor y is a subset of y. Here is another such. Neither is x a subset of y nor z a subset of x. But here, if you take something bigger like this, these two are connected. So whereas y is subset of this, you don't have such relations between x, z, x. Let me make this a little bigger. Okay. So you don't have such relations between x, y or z, y or x, w, z, w. You have no other relations. So we often say x and z are incomparable. They cannot be compared. Or same is true for x and y. The same is true for x and w, z and w, z and y. They are all incompatible. So, and we often write it by saying like this. Okay? So that's so trichotomy means that there is any two are related, they are comparable. But if it is not trichotomous, it means that there can be things which are not related. That's the whole idea. Okay? So it comes, as I told, a total order is a trichotomous per partial relation. So a partial order. So for instance, less than or equal to is a example of such a thing. Next.
Thank you, Doctor.
Now 4.1.1, so that is the reflexive relation. As I was telling last time, reflexivity geometrically you can think of, if you think of this square and then the diagonal of this square. So any relation, any subset or sub-figure of this square which contains the diagonal this is a picture of a reflexive relation. This is the picture. For symmetry, you can do the same thing. So symmetry means that you should have the diagonal as its line of symmetry. So that means it would be something like this. Now I have to be careful. I have to be careful in trying to draw this. Something like this. So the diagonal symmetry means geometrical. If you want to have a geometric picture, the diagonal must be a line of symmetry. Okay? Transitivity is a little further thing. You need to have a three-dimensional picture, but let me it is a little bit difficult. So what I tried to say in this 4.1.1 is that given any relation, you can always make it reflexive. You can, and the best way you can do it is you join the diagonal. Now, you can write the proof of this now, right? Okay? Are you okay with it?
Yes.
Okay. Let's come to 4.1.2, section 4.1.2. The idea is the same. It says that symmetric, if and only if you have this. So, if you join its opposite, okay, its opposite, the opposite relation is nothing else, but you take the reflection of the original relation on the diagonal. So, and if you join these two, that will become the smallest symmetric relation containing it. So, that should also be clear, right? Okay, you should be able to write the proof of 4.8 and 4.9. Yeah? Yes or no?
Yes.
Or okay, but I'm saying you first try to submit these proofs, and then you will see my feedback, and then you will slowly reframe them. So rewrite them, and will slowly become better. Now let's come to 4.11. This one is I'll give you the idea. See, what is transitivity? So when do you say that R is transitive? Is this condition? Yeah?
When A is related to B and then B being related to C, which automatically means A is related to C.
Correct. So A is related to B and B is related to C. It means that A is related to C. Good. But let's see what is it kind of saying. So let's try to pick up some. So I may not be given a transitive relation, but what am I trying to do? I start off with an A. And then I find a B, so I'm joining it by a line saying that it is connected. Or let me write it like this. So A is related to B, okay? Then you are saying that it's related to C, okay? My understanding is that if I call these as paths, then you compose these, follow these paths, so you have the next, so you have a path from A to C, correct? Now what you are telling me is if C is further related to D, so A is related to D, B is also related to D, right?
Yes.
So what will you do? You will try to find all these possible paths starting from A of finite length. Okay? Now there can be several paths starting from A. There could be paths also from C. So you will take all of them. Okay? So now let's see how do I do this? So how do I, this is already there. So this corresponds to AB. This composite path corresponds to AC, which is in R composed R, right? This pair AD is going to come from R composed R composed R, so you do it 3 times, right? Okay? So what I am saying is, because see, this condition don't tell you from where you start. So this you are going to do for all possible A's in your set A. So what is the end result? The end result is that you will have these elements. You will have all these elements like this. You will have all these elements like this. So you are going to collect all these elements. R composed R, R composed R composed R, and so on. You have done this n times. For each n, you are going to do it. And when you get this set for each finite n, that's what you think, and that's exactly the place where it will happen, that if you take any two which are related, like, so if this big set is what you called S, then automatically you should have ASB, because ASB means it is in what will it mean? ASB will mean it is in one of these composites. So AS means that it is an n level path possible. So in between A and B there are n points, right? Each of which are related by R. And you further tell me it is C. So from A to B you have a path of length n, from B to C you have a path of length m, and if you join them, you have a path of n plus m. So this tells you that A must be related to C. Okay? So this is the rough intuitive idea of the proof. What you collect, you go on collecting. So you take on things which are related by R. So composites, you take composites and then composites and then composites, further composites, and whatever you get in the total collection is what you say to be the next relation, that is. And that does the magic. Okay? Now this is all diagrams and stories. How do I write this in formal, as I said, mathematics is formal manipulation of symbols. So I have to put it in a very, very crisp way, and that is what is done in this is done over here in 4.12. See what is it saying. Definitions like Rn are often called recursive definitions. I'll give you have seen this recursive definition before. You have seen this. I'll give an example. For instance, when you define the function, one of your first examples was 2x plus 1, right? One of your first examples possibly, right? What is it? You are told, you give me x, multiply it by 2 and add 1. Very good. But then, after some time, you are also given a function like this. Do you know what is this? N factorial, right?
Yes.
And how was this defined? Well, now it's a big thing. So, you say 1 factorial is 1, 2 factorial is 2 into 1,
Times
3 factorial is 3 times 2 into 1, and so on. You will say n factorial is n times n minus 1 into n minus 2, and so on, 2 into 1. Now this ellipsis business is just nonsense. It doesn't make any sense. I don't know what is it. So what is this I can rewrite? I can rewrite this as 2 times factorial 1. I can rewrite this as 3 times factorial 2. So this is actually nothing else but n times factorial n minus 1. And that is exactly your definition. So this is 1 if n is 1, and n times factorial n minus 1 if n is greater than 1. See, it is this. Now what's the problem between this and this? The problem is here. So in the first one, you give me an x, I immediately can find out what is it. I multiply it by 2 and add 1 to the result. Very good. But you give me a number n, I cannot immediately say how do I find factorial n. I'll have to know the answer of factorial n minus 1 first. To that result, I'll have to multiply n. Now, how do I know n minus 1 factorial? Well, to do that, I'll have to know factorial n minus 2. So, you see, it is going back to the same definition. Right? But at each stage, we see that it is of a lesser complex. The numbers are getting smaller. The first one is often called the seed condition. It stops over here, so that is called the seed condition. And this one is called the recursive relation. So what is a recursive definition of a function? Well, it is function defined using itself again. So it is not as explicitly, this one is an explicit definition of a function, but this is not that explicit, it has to be worked out. If you think in terms of programs, how does a program tackle this? Well, it is kind of a stack. In programming language, it is usually called a stack. So, and it goes down, it goes on building this stack, it goes on and on and on until it comes to the seed stage. It evaluates at the seed stage and then goes back to evaluate the answer. Alright? So finally it knows what is 1 factorial, multiplies it by 2, multiplies it by 3 and so on and so forth, and finally it knows the answer of n factorial that it knows. Now this is also a recursive. So that's another example. Here is another example of this recursive definition. So Rn, this is R if n is 1, and this is R composed Rn minus 1 if n is greater than 1. Right? So how do you start? That's exactly what you do. So, suppose you want to find R composed, say you want to find R6. So that is R composed R5. This is R composed, but no, you know that it is associative, so you can carry on. Doesn't need to put the brackets. So this is R composed R4. So this is R composed R3. R2. This is R1, but I know R1 is R. So this is my evaluation step. The last step is the evaluation. So this is what I was saying intuitively, the 6 stage, the paths of length 6. So I compose R 6 times. So that is my Rn. Okay? So what is this? So Rn is nothing else but you compose R n times. And then this R tran, what is written over here, is just that union. So what I wrote there is what I said over here is R tran. Right? So it is just this union, this collection of all those paths, as I was saying intuitively. Okay? So that is this. And then the rest follows. Now the question over here is, I used mathematical induction. When in section 2, in chapter 2, I'll speak in detail about mathematical induction and so on. I'll also show it's there. It's recursive functions cannot always be defined. It can be defined only at places where there is some kind of a mathematical induction or some such tool which helps you to say, so as I was saying, it gets less complex. You are not very, this evaluation of factorial n didn't bother you. It should not bother you because you know at every stage it is getting smaller and smaller. So this way of making it less complex, this is exactly what this induction principle is about. So we will see that things about natural numbers are very, very much dependent on this strange principle which is mathematical induction. Everything that we say about natural numbers is essentially induction, nothing else. Okay? So, but we need to use induction quite a few times to get this understanding. So this is a very, very condensed, I don't know how will I be able to write this out, and that's why possibly the contact classes are better, because there in this class people will actually explain this. It's very difficult to write all of this down in a note, but you see the idea and how is it framed in terms of formal induction. The full thing, understanding induction, will come at the end, but suppose you know it, I know that you have heard about mathematical induction and you know something about it, so I just used it. Yeah? So is this part now clear? Do you get the meaning of this Rn that is given? And yeah? Am I alone or am I with you all?
Yeah, we can hear you, Doctor. Yes.
Yeah, so is this clear? Is this Rn picture clear?
Yes, it is, Doctor.
Yes, it is.
It is now.
Now go through this notes, and you should definitely come back with more queries. I expect them. And then I have given in this lemma, I have given this proof, as I said, by using mathematical induction about what I said intuitively, that this what will be A, so as I was saying, what will be ASB, these are all the, so there exists a path of some length from A to B, as I was saying, using this pictorial language. That's what it is used over here. Go through this proof, and then later on I have put in indexed sets and an annotation about what mathematical induction is. Okay? So this one I would ask you up to 4.16, that means before, just up to 4.1.4, equivalence relations. Just before that would be this week's work, and you read this last section, 4.1.3. If you can understand this, very good. So there is, I believe there is nothing left to for you to complete over here, but you might write out your own proof and send, let me see if you understood it. So you can submit that, and I can go through that. So that and everything which is left to you for exercise, left as an exercise and so on, up to 4.1.3, you should submit next week. Okay? Okay?
Okay. All right.
Submit as a LaTeX file, LaTeX PDF file.
Okay, so can you repeat on the question that we need to go through?
Which one?
The question that we are supposed to submit.
Yeah. So you have the lecture notes with you. Up to 4.1.3, there are several places where you will see the words left as an exercise. Okay? Written. Say for instance, in corollary 4.6, you will see left as an exercise. Okay?
Okay.
Theorem 4.8, immediate from definition, left as an exercise. Okay? So all of this, when you submit this, as I said, from chapter 1, all your submissions will come for assignment 1. So it will have that unique assignment number for assignment 1. And your submission will be, say, Theorem 4, corollary 4.7, your answer to that. So you write down that statement and you give your proof. Okay? So whatever is the proof, you fill it up. So that will be your submission. And I insist, your submission should come as a typed LaTeX. So LaTeX typed PDF file. Type it in LaTeX. Run PDF LaTeX. So a PDF file will come out. That should be it. Okay?
Doctor, can we submit it in writing, because I've got problem with I can't install LaTeX on my laptop because it's a work laptop and it doesn't allow me to install certain things.
Oh, but exams, I believe, you'll have to do it, and that is why because you see now UNISA exams are no more going back to the old format. It will be online, and online means you will have to submit an essay. An essay means that now it is it is underway, but I believe it is from honors level. There is no way that you can escape, because you are already learning LaTeX in an HRM module. Now I understand your query. There is a site. You can access the net, can you?
Yeah, the only thing is I've already done half of this assignment in writing. What I can do is, I'll speak to my boss and I can get LaTeX, but can we maybe start submitting in LaTeX from the second assignment?
Okay, that's fine.
Because I've already done so much of the first one in writing.
Okay, that's fine. But what I'm saying is, you need not actually, because LaTeX is a huge thing. If you have, it's a huge system. So what I would suggest, on the other hand, if you don't have it, there is but if you have internet connection and you can work on that, there is something called Share LaTeX. Share LaTeX.
Okay.
And it is, so you can open your account there. It's free. You can open your account there, make your submission there, and send me the link. You don't even need to send any email or so, or compile it. You can send me the link to that project or file. I'll get the link and I'll correct it there. And that can be done for your final exam submission also.
Okay, thank you.
So that will not need any LaTeX on your machine, but you can have it on the site. on the shared LaTeX site. I'll also send a link to this shared LaTeX site and a kind of a help for that on the shared LaTeX site itself with this next announcement that I'll post by tomorrow.
Okay, thank you, Doctor.
Yeah.
Okay, a question for myself.
Yes.
Because I'm still going to learn later. I'm not taking the HRM module this year, so I'm gonna learn it on my own. Is the due date for this assignment still the 30th for the first assignment?
As I said in my first, as I started, and Julia was late, and I think you were also late. Forget about those. So forget about those deadlines and so on. I don't mean to say that those assignment questions have to be completely forgotten. The reason is, what we are going to do is essentially those same questions, but in a much more structured way now. Okay? And we'll be doing much more. So, if you submit your weekly things that I am saying now, well, that will be fine. So, if you cannot submit say next week, you let me know. So, you have 2 weeks thing to submit the week next. You get me?
Yeah. With me, the problem is that I'm still going to learn LaTeX because I haven't done it before. So I still have to learn it and keep up with the assignments.
Okay, with my announcement, I think I will be able to also shed some light on this. The shared LaTeX thing, as far as I used it long time back. So when I was here and I don't remember now, some 4-5 years back with one of my students. But as far as I know, he learnt LaTeX from there itself, and initially you don't need to learn LaTeX for that, for shared LaTeX. You will be automatically given a kind of word-like interface or something, and you will slowly learn it from there itself. So you need.
That's fine. I do have it on my computer, but I haven't learned it. So
okay. But if you use shared LaTeX, it will be much easier.
Yes.
Yeah.
I'll do that. Okay.
Yeah. Okay. Yeah. Any further questions? First, I stop recording then.